So thank you for inviting me. So I thought I'd start this talk on pilot wave hydrodynamics by discussing some of my career paths so far. There have been a few bumps along the way, and I think it's quite informative to understand how I went from being an undergraduate student to being an instructor. And so I started off by taking my undergraduate degree in mathematics, and I think because I wasn't very keen on taking exams, I wanted to see if I could explore research problems in a wider setting. And I did two summer research internships at William Hill Bookmakers, which was a very interesting experience working on statistical modeling of sports matches. And really from these experiences, it definitely affirmed to me that I enjoyed working on longer term problems, and I was interested in exploring ways in which I could avoid exams and instead work on projects. And so after I finished my 3-year undergraduate, I did a master's at Oxford in mathematical modeling and scientific computing, where I was able to explore problems now rather than statistical modeling. I was able to work on physical modeling. And what motivates me in particular is working on problems which I can see with my eyes. So I was working mainly in geophysical flows. So here on the left, we have roll waves, which any of you who live in rainy cities with hills will have seen roll waves often. And also I worked on glaciers as well. It was so I had a real mix of statistical modeling and physical problems. So after I finished my master's, I moved to Bath and I started working with Paul Milewski in pilot wave hydrodynamics, which is the interaction of a droplet with its self-generated wave field, which I'll be talking about more of the details very shortly. And while I was at Bath, I managed to spend, as I was part of the statistical applied mathematics program, combining my interest in statistical and physical modeling. And I managed to spend 3 months as a visiting student at MIT, working with John Bush and Ruben Rosales, where MIT is one of the hubs of the pilot wave hydrodynamics community. So this time at MIT, it actually served as a 3-month-long interview for my current position as an instructor in applied mathematics. So an instructor is kind of a mix between a postdoc level and then lecturer responsibilities. So I do research in addition to lecturing courses and supervising students. And while I've been at MIT, I've really been trying to broaden my research, building off the work that I've done in pilot wave hydrodynamics. So for example, I've been working in Faraday pattern formation, which is quite an old problem, but one of the novelties we've been looking at, motivated by the pilot wave problem, is the influence of submerged wells, these black circles here. And you can see if you arrange these wells in a special way, then you can get very interesting here, like a laser-like pattern appearing. Also, I've been working now on dynamical systems, and more recently, I've started looking at lattice dynamics, which is a problem I'll talk about today. But one thing I found is that my path forward has been quite unclear at times. In my undergraduate, I spent a lot of time playing my trumpet and rowing, and ended up getting a 2-1 rather than a first, which was what I was aiming for. And so then it became a bit unclear to me whether, well, first of all, whether I was good enough to actually do research, and if I was good enough, would anyone still want me to do research with them? And well, it turned out that actually that didn't matter so much, because my ability to perform in exams is somewhat independent of my ability to do research. And I think what I've learned from these experiences is that even though the pathway forward can be quite unclear at times, if you're motivated by working on problems, then you can kind of overcome some of these uncertainties. And in particular, the first option isn't always the best option, or the first idea that comes to mind isn't always going to be the way forward. And so this has really led to my work on pilot wave hydrodynamics, and I'm very excited to share with you today some of the very rich problem of this droplet interacting with a fluid bath. So this field of pilot wave hydrodynamics really combines two different fluid mechanical problems. So first of all, we have Faraday waves, and the second point of interest is looking at droplet dynamics. So with Faraday waves, we consider here a fluid bath, where this bath is a viscous bath, and you can vertically vibrate this bath. And if you vibrate this path with sufficient vigor, then the horizontal rest state can destabilize, and instead we get the emergence of these standing or Faraday waves, where these Faraday waves are characterized by two important features. So they have a fixed wavelength, which will be a feature that is important later in this talk. And also these standing waves in this particular parameter regime have the frequency which is half that of the frequency of the shaking. So these Faraday waves I mentioned before, and this is a very well-established field, but in 2005, Yves Goudert and Emmanuel Faure in Paris discovered that these Faraday waves can actually give rise to a very rich range of dynamics, where here we can see what happens when one pokes the surface of the bath, here at the top with no vibrational forcing, and here at the bottom, just below this threshold, which standing waves appear. And we see that in the wake of this propagating wave, we get the emergence of these standing waves, and these standing waves can actually lead to a remarkable range of dynamics. So here we see that we can have a droplet bouncing indefinitely on the surface of a fluid bath. So the droplet here doesn't actually coalesce with the bath at all. There is a very thin nanometer scale air layer separating the droplet from the actual surface of the bath. And due to this vibrational forcing, the droplet doesn't coalesce because the shaking of the bath up and down means that the droplet is propelled back into the air before the coalescence time, or before the time scale over which the air layer depletes is reached. So this bouncing dynamic is very rich. It's a completely stable dynamic. Goudert's group managed to show that you could actually keep these droplets bouncing for 3 days if you wanted to, or even longer if you had the inclination. And one thing that they discovered was that actually, if you increase the vibrational forcing even further, but keeping it below this Faraday threshold, but approaching it very close, you can actually get an instability of this bouncing motion. And rather than having stationary bouncing, we can get this motion in which the droplet is propelled across the surface of the bath. So what's fundamental here is that at each impact, this droplet, you can think of it as a local exciter of waves, is generating these waves, these Faraday waves, these standing waves with a fixed wavelength and frequency. And the slope of these waves is then propelling the droplet. And the slope of the waves is the waves generated by all prior impacts of the droplet. One central feature of this dynamic is path memory. So as one increases the vibrational forcing, getting closer and closer to this instability at the Faraday threshold, then the memory time increases, and so the droplet remembers a greater duration of its past. So two fundamental features here, path memory and the fixed wavelength of the pilot wave. And in particular, experimentalists have performed a remarkable series of experiments, starting off with Goudert's group and later John Bush's group at MIT, in which we're able to show that there are connections between this fluid mechanical system and quantum phenomena. So here, for example, we're able to show that if you consider some of the canonical quantum pictures, so if you were to start off with, for example, Schrödinger's equation and consider a harmonic potential, then actually the results predicted by Schrödinger equation have, in some extent, when one uses one's imagination to think freely, that actually you can show some analogies, for example, here with the double quantization arising from Schrödinger's equation with a harmonic potential, a very similar feature arises in this walking droplet problem. Other examples include tunneling, unpredictable tunneling across submerged barriers, Zeeman splitting, Landau levels, Friedel oscillations, and another problem that I'm going to talk about today is Wavelike statistics in a circular corral. So I should emphasize here that this is a fluid mechanical system, and I'm not saying that these walking droplets are quantum mechanics. I'm simply saying that there are some analog behaviors. So what's the significance of these analogues? Well, de Broglie imagined a pilot wave system back in the 1920s, the predictions of which led to him receiving a Nobel Prize. And here now we have a physical picture of what a pilot wave system could look like in the quantum scale obviously there are some important differences. But it's important here that we have a physical picture of wave generation, which is something that de Broglie didn't specify in his double solution theory. And we also have this notion of how the droplet is actually guided. So there are important questions that researchers are asking in terms of looking right at some of the philosophical aspects of quantum mechanics and revisiting some of the notions of the Copenhagen interpretation. And so this is a very broad and also provocative problem. So one of these problems that I'd like to share with you regarding some of these dynamics of droplets. So here we have the emergence of wave-like statistics in a circular cavity. So this is a three-dimensional cavity, a circular well, and it's submerged below the surface of the bath. The submergence is due to meniscus effects of the waves if you have a wall breaking the surface. And due to the reflection of the waves across the step and the damping in the shallow or beach region, the droplet is actually confined to this well. And here we see in this movie, we can see this confinement very clearly when one strobes the droplet's vertical motion at the bouncing frequency, where here the droplet appears to glide across the surface of the bath, guided by the slope of the waves generated at all prior impacts. So what are the dynamics of this system? Well, it's shown in some remarkable series of experiments that as one increases the vibrational forcing, or equivalently the path memory, so the number of prior impacts that influence the droplet's path, we get a series of different transitions from circular orbits to a series of precessing trefoil-like structures. And in long path memory, so when many previous bounces influence the current trajectory of the droplet, we get this transition to chaotic dynamics, which we see here on the right. What's the dynamics of this chaotic behavior? Well, we see on the left here a time series of what the trajectory looks like when color-coded by its speed. And after a long amount of time, we see a transition in which actually there's some kind of correlation here between the different colors. If you maybe squint your eyes a little, you can see that there are some darker blue circles appearing corresponding to the droplet moving more slowly. And if you then look at the probability density function or the histogram of the droplet's position over this long amount of time, we get this wave-like statistical form, which actually you can argue has an analogous form to if you were to take Schrodinger's equation and solve a particle in a box or a circular box in this case. A second important analog arising in these bouncing droplet dynamics was first explored by Emmanuel Faure and Couder's group, and more recently by John Bush's group, and this concerned the dynamics of droplets walking in a rotating fluid bath. So here on the left, we apply this bath to a rotation about a vertical axis, and we find now that there are, well, when you consider the frame of reference rotating with the particle, there are Coriolis force and centrifugal forces arising, but the centrifugal force actually cancels, its contribution really cancels with this parabolic profile of the waves generated by the rotation. So really the important thing here is that there's a Coriolis force applied on the droplet. And if one starts to think more broadly in terms of quantum phenomena, then actually the form of a Coriolis force is similar to the Lorentz force on an electron in a uniform magnetic field. So this connection is very important. And one thing that's been explored in experiments is, well, if we've got this connection to quantum mechanics, is there going to be some kind of analog to Landau levels? And will there be some kind of quantization arising in the orbital radii arising in the walking droplet system? So here in this figure, we explore the effect of the strength of the rotation on the horizontal axis and the resultant orbital radius seen in experiments. And as one increases the path memory or the vibrational forcing, we see that this is not just experimental, any experimental slips. This is a really robust phenomenon in that we have these precise orbital levels arising. And these orbital levels are discrete. As you increase the path memory further and further, then these discrete orbital levels become more and more pronounced. So here these dashed lines are separated actually by half the wavelength of the Faraday wave. So this fixed wavelength that we discussed with the arising as a consequence of the Faraday wave dynamics is fundamental here to this quantization, this discrete orbital levels arising in the walking droplet system. So here we see these orbital levels in more detail. So this is really interesting that we have this analogy between the walking droplet system and Landau levels in quantum mechanics. But one question then is to ask, well, what happens when you reach the regime in which these circular orbits are unstable? So when you drive the system at very high vibrational forcing, or equivalently, you're exploring the regime in which the path memory is very long. Well, here actually, just like in the previous problem we looked at with the submerged cavity, we get a transition to chaotic behavior. So here we see on the left, if you're driving at low forcing, we just get these circular orbits. But as one increases the vibrational forcing, then we get these chaotic behavior arising down here in the bottom left, where it looks like some kind of spaghetti, but actually when you consider the instantaneous radius of curvature of the droplet motion, then we see rather crudely perhaps in this picture, but we see that it constantly jumps between different fixed values. So we have one level, another level over here. And when you look in at a very long time and consider the statistics of this problem, one actually realizes that the droplet path is switching intermittently between these orbits of different radii. So all of these dynamics are unstable, but they're weakly unstable in this regime, and we get this intermittency. And the result of this intermittency between these different orbital states is the emergence of this wave-like statistical form. So perhaps even in this spaghetti on the left here, you can make out small circular orbits, and then at other places you can maybe see some larger orbits corresponding to different peaks in this histogram. So this is a problem which is being explored a lot theoretically as well, and these results are very robust. And it's somewhat remarkable that we get these very rich dynamics where the two principal ingredients are the path memory of the system, in particular looking at the long path memory limit, and this wavelength of the pilot wave. So some of the questions that one should ask here is always don't get too overexcited. And let's just think carefully about what we're saying here. So we have some similarities to quantum mechanics. We have a particle and a wave interacting, the particle here being the droplet, the waves being the Faraday waves. And the existence of the droplet and the wave is mutually dependent. If we were to take away the wave field, then this droplet would just splatter on some solid surface. If we were to take away the droplet, then there would be no generation of waves. And in terms of at least a qualitative sense, we have the emergence of quantization and wave-like statistics. Important differences, and these differences are fundamental. We're looking at a fluid mechanical system on a macroscopic scale rather than looking at a quantum system on a quantum scale. And this is a dissipative system. The fluid has got a non-negligible viscosity. And so if we were to just remove the droplet at any instant in time, then these waves would just decay. But this system is sustained by the external vibration of this fluid bath. But one question that one can think about, and this is really the motivation for all of these different quantum analogues, would be what is the class of quantum phenomena that can be explained by classical mechanisms. So the dynamics of this pilot wave system and making these analogies with quantum mechanics is very rich, but also one can explore this pilot wave system in very different settings. So some work that I was working on recently was connecting pilot wave dynamics to the Lorentz equations. So Lorentz equations is a canonical example of chaotic dynamics in dynamical systems, first discovered by Lorentz in 1960s. And here to try and explore some of the dynamics of this pilot wave system, I considered the most simple model I could construct that would have the relevant features of the walking droplet system. So here we have in dimensionless form two equations. So the first is the equation of the droplet position. And here we have an inertia term balanced by a drag on the droplet And then we have a wave forcing. So here we can imagine this wave field H as a dynamic potential. So this potential is evolving in time according to the generation of waves by the droplet. Or in here, I'm considering really an idealization, so I'll refer to the droplet as a particle. So in order to strip this problem down to its bare essentials, I considered a wave field that was just one-dimensional. So here I suppose let's have a sinusoidal wave field, where at each impact we're creating waves which are just cosines centered on the instantaneous position of the particle. And notice here that we're considering a sinusoidal wave field, so we have something which has got a fixed wavelength, just like with the walking droplet system. Another important feature here is the decay of these waves over time. Here that decay rate, at least in dimensionless form, is given by mu. So as mu goes to 0, then we approach what would be the equivalent of the Faraday threshold. So to give an example of some of the dynamics arising in this system, so if one were to drive this, if one were to have a long or a very large decay rate of the waves, so a very short memory time, then the particle is just at rest. It sits at the top of its sinusoidal, well, its cosine wave, and any perturbations to this state just results in a translation of the system, and the particle remains at rest. As one increases the length of the path memory, here increasing this parameter gamma, then what happens is we have a bifurcation, and this particle is propelled now by the slope of its sinusoidal wave field. So I wanted to explore the dynamics of the system, but in its current form, it's somewhat difficult to understand what's going on. We have this memory-driven system, we have this integral over all prior impacts, and I wanted to try and simplify this system into something a little bit more recognizable, the result of which was connections to Lorentz equations. So I didn't know this connection at this point. I was just trying to simplify a mathematical problem into something more tractable. So we know here that we have a sinusoidal wave field. So what I did was to represent the sinusoidal wave field in the frame of reference of the particle as the sum of a cosine and a sine, where A here, you can regard this as the local wave amplitude, because if you set x is equal to xp, then you just get h is equal to a. And the B here is the local wave slope if you were to take derivatives with respect to space and then evaluate at the particle position. So if you express the wave field in this way, then after a little bit of mathematical manipulations, we can transform the integral into a series of differential equations. So we have now a four-dimensional dynamical system for the particle position, the particle velocity v, the local wave amplitude a, and the local wave slope b, where one of the important features here is that by translational invariance of this system, actually we can cut out the particle position from the system of equations, and we have a three-dimensional dynamical system, which is driven here by particle-induced wave generation. So notice now that memory here is appearing as these damping terms for the local wave amplitude and local wave slope. So I was exploring the system for some time and trying to understand the dynamics. Dynamical systems are one of my favorite topics, and so I had a lot of fun exploring the system. But then one day I noticed that we have a three-dimensional system with two quadratic nonlinearities, these VB and VA terms. And actually, somewhat surprisingly, and this is a very good day of research, was that if you do a change of variables, you can actually transform the system into the Lorentz equations. So I haven't written down the transformation here, but we have these three parameters, sigma, rho, and beta in the Lorentz equations. And you can write these parameters in terms of our parameters of the Pilot system. So this dimensionless mass, kappa naught, and the dimensionless decay time of the waves, mu. So what can we do about the fact that we have this connection to the Lorentz equations, where there are thousands and thousands of papers on the Lorentz equations? Well, we can use this correspondence to try and identify new pilot wave phenomena. Because we have a very complicated system, it's very much plausible that some features have been missed in prior studies, because if you don't know a feature's there, then you won't look for it. And so now I was able to make quite a lot of progress just by understanding what had been done in the Lorentz literature and seeing how to interpret these dynamics in terms of pilot wave systems and vice versa. So some of you will be familiar with dynamical systems who recognize this regime diagram for the Lorentz equations. So the remarkable series of transitions that arise before the canonical chaotic behavior arises as one increases, at least in this case, the Rayleigh number. In the context of pilot wave dynamics, this increasing this parameter is essentially the same as increasing the path memory. And so now we can place on this map, at least sketch at least, some of the different dynamics that arise in the pilot wave system and how they relate now to Lorentz. So we have this stable fixed point at the origin, but this exactly in our pilot wave system is this rest state that we looked at before, where the particle is stationary and just sits on the top of its cosine wave field. Then this is bifurcation to steady propulsion, which we also looked at. And one thing we haven't considered is actually there's this destabilization, the long path memory limit, in which we have this subcritical Hopf bifurcation and the walking dynamics, the steady propulsion becomes unstable. But these features have been covered in some prior studies, but one of the new things we were able to learn from this analogy with the Lorentz equations is that there's this homoclinic bifurcation in the Lorentz system. And this is fundamental. It gives rise to all of the interesting dynamics arising in the Lorentz attractor. One of the things that actually I found when you looked at this homoclinic bifurcation is here it gives rise to these what are referred to as jittering modes. The droplet executes a stepwise motion across the surface of the bath. Here it's stationary for a long amount of time, building up its pilot wave before finally it zips down into one of the neighboring troughs, and then the process repeats. So this was a very nice physical interpretation, which is something I found hard to understand, at least mathematically, from the Lorentz equations. And another feature that arises in the system, which was, I didn't think to look at it until I learned about Lorentz equations some more, is coexisting attractors, which is something being reported in some simulations of pilot wave dynamics, but it wasn't, at least in my mind, a strong mechanism for why this arises. But now in the context of the Lorentz equations and one of the consequences of the homoclinic bifurcation, actually these coexisting attractors, here we have steady propulsion and chaotic dynamics at the top, and steady propulsion and periodic dynamics on the bottom, is now actually on far more familiar territory. So it's also natural to ask then, well, these are some of the dynamics that arise in Lorentz equations and also the pilot wave system. What do some of the chaotic dynamics look like with this pilot wave system? Well, here I explored for fixed memory some of the different chaotic attractors that arise. And one thing that's very noticeable actually in specific parameter regimes, where you can link these parameter regimes between the Lorentz system and the pilot wave system, is here on the bottom projection of this three-dimensional phase space, we have the Lorentz butterfly, this canonical feature, but here just by the change of variables, the butterfly is upside down. But one of the things that Lorentz showed is somewhat remarkable is that actually this chaotic system, you can gain a lot of insight by considering the Lorentz-like map. So here you can, the analog in this system would be considering consecutive maxima of the local wave amplitude, plotting the relationship between these consecutive maxima, which somewhat surprisingly actually forms, at least on the eyeball scale, a continuous curve. And actually these curves have cusps, where these cusps actually play an important role in the pilot wave dynamics. Here in red, we have regimes in which for a particular, when you achieve a particular local wave amplitude, when you reach the next local wave amplitude, the particle will still be traveling in the same direction. The blue dots correspond to when you reach a local maximum in the wave amplitude. By the time you reach the next maximum local wave amplitude, you'll be traveling in the reverse direction. So actually now, just by considering this map, we're able to gain a reasonable insight into some of the dynamics of the system, whereas it was somewhat inscrutable when trying to explore the system as a memory-driven dynamical problem. So some of the questions that arise from the system be, maybe we have a system which has got statistics as well as problem we've looked at earlier in the talk. And so what are the connections between the dynamics and statistics? A problem that I'm exploring with an undergraduate student as well is what's the influence of applied potential? And more recently, I've been looking at, do similar connections arise in two spatial dimensions? So there's something called the complex Lorentz equations. And I'm trying to see if I can connect the complex Lorentz equations to the pilot wave system. So one last connection of this pilot wave system to different areas is a connection to collective dynamics. So this is a problem which has grown in the last few years, particularly work by Pedro Sainz, showing these spin lattices here, where we have droplets in this bottom left, all interacting, where each droplet is confined to a submerged world, but they still communicate through their shared wave field. We can also get these different rings and square lattices appearing. And then for adventurous experimentalists, you can consider Archimedean type lattices. And one problem that I've been looking at recently would be some of the swarm dynamics that can arise when you have lots of droplets interacting in close proximity, all communicating through their shared wave field. So one problem in particular I looked at was in collaboration with Stuart Thompson, one of my fellow instructors at MIT, and Ruben Rosales. And this concerned experiments that Stuart did where we have multiple droplets interacting in a submerged and the channel. So here we have these ring of droplets. They form an equispace lattice at low vibrational forcing. But as one increases the vibrational forcing, so increases the memory, we get an instability. And we get these oscillations of these droplets. So the whole lattice is communicating through this wave field. And the result is, and here we have out of phase oscillations between neighboring droplets, but actually a far richer array of dynamics can arise. So one feature of the system actually, so here we have for 20 droplets, we get these out of phase oscillations. The Stuart was able to show that if you have 40 droplets in specific regimes, I think it took him a while to set up the experiment, but here now we have these droplets. Again, this is a video which is strobed at the bouncing frequency. And as you increase the vibrational forcing, they start oscillating, and then this solitary wave breaks out. There's a remarkable feature here where we have these droplets just going round and round, and this is a completely robust phenomenon. So some of the work that we wanted to do then was trying to come up with a rationale for when these solitary waves might arise, and then also when these vibrations of neighboring droplets emerge and are stable. So we tried to develop a theoretical framework where here we have, just like in before, we have droplets being propelled by the slope of the local wave field, where here we have this in a slightly different form. We have that this wave field can be regarded as a dynamic spatially periodic due to the periodicity of the lattice. We're considering here circumferential motion, and also non-local. So here we have non-locality in time due to the memory of the system, and we also have non-locality in space because the waves generated by each droplet at each instant in time have a spatial extent, and this spatial extent then leads to the communication between these different droplets. So this system we were able to explore, and for instance, explore some of the onset of these different vibrations, whether we had this solitary wave appearing or this stable vibration of neighboring droplets. And in the latter case, we wanted to see whether we could come up with a theoretical framework that would be maybe slightly more simple, at least conceptually, than the full pilot wave system written down here. So one can show with some weakly nonlinear analysis that actually we can write down a system of amplitude equations, where here A is the complex oscillation amplitude of each droplet, the nth droplet on this periodic lattice, and B is the drift of each droplet over time. And where here, due to the discreteness and periodicity of the system, we have here finite difference operators rather than having derivatives because we have a discrete quantity. So here actually we have what would be a discrete Ginzburg-Landau equation, the first equation. Ginzburg-Landau is a canonical equation which appears in a huge number of fields, but here looking in a discrete form derived exactly from our original equations. And this Ginzburg-Landau equation is coupled to a diffusion equation. So if you were to ignore these bottom two terms here with the A's, then we just have a diffusion of the drift. And then we have this Ginzburg-Landau equation describing the amplitude. So this work really put the dynamics of this lattice onto the collective dynamics map in terms of we now have something which is a canonical feature to many systems now in the context of pilot wave dynamics. So in particular, we can use this framework for trying to understand some of the dynamics that arise in our simulations. And so we can explore, for example, what happens as one increases the path memory, and we saw a remarkable number of transitions between traveling wave solutions, some breathers, these are dark breathers, dark solitons, and also bright solitons. And so some of the questions to ask here would be, well, we've iterated now from experiment to theory. Can we now iterate back to experiments and see whether some of these very specific features actually arise when you do in a laboratory? In particular, we have some interesting bifurcations between these states, and also more broadly, here we've looked at a very specific set of equations for these lattice dynamics. In a more general context, what class of discrete dissipative oscillators exhibit similar behavior? So I was going to stop there now. I could talk about this problem all day, but for me, pilot wave hydrodynamics represents a really rich field which connects fluid mechanics. For example, there's lubrication theory arising in the air layer between the droplet and the bath. There's Faraday waves, the droplet dynamics, droplet deformation. Then dynamical systems. Well, here I've just given one example of how you can connect to Lorentz equations, but more generally, there's connections to periodic orbit theory and similar systems. Quantum mechanics is a very evocative part of pilot wave hydrodynamics, and it prompted lots more research. And then more recently, as I said, we have these researchers working on collective dynamics, providing an example of a system in which all the constituents of the system interact through a shared self-generated wave field. So I'm going to end this talk on a couple of questions, which might never be answered, but are important things to think about. So could a physical picture for quantum mechanics take a similar form to this interaction of this fluid mechanical microscopic droplet and its Faraday waveform? I don't know. I'm not saying that the answer is yes. Time will tell, but it's certainly an important question to ask. And then as well, if we have these connections to quantum mechanics, well, we've seen that Schrodinger's equation does a very good job of describing the ensemble statistics of non-relativistic quantum mechanics. Could there be some kind of analog to that in the walking droplet system? So thank you, and I'd be happy to take any questions.
Thank you very much, Dr. Durey. Very interesting presentation. And thank you also for the insights on the academic career path, which can be useful to our audience. I can see that some questions have already been answered in the presentation, but if there are further ones, please post them through the Q&A box. So I guess our first question is there a known limit to the length scale of this sort of problem based on the absolute or relative size of bubbles and tanks?
That's not something I've considered before. The length scales in this problem are really very much defined by the fact that surface tension is fundamental in this problem in allowing for the droplets to bounce. And so you've got to be working on a small enough length scale so that surface tension is a critical feature. So really that's the main confinement of the length scale of the system. I think when I was first imagining this system, I was imagining footballs bouncing along some big field, but actually we're working on this millimetric scale, and that's mainly due to surface tension.
Thank you. And another question is, have you investigated these kind of problems in a stochastic setting through the use of random variables?
Actually, yes, so something I looked at a little bit in my PhD, with Paul Milewski and John Bush. And we found in some particular regimes in the high long path memory limit, we have this form where this pilot wave actually can be decomposed into two timescales, a timescale that's evolving very, very slowly, and a timescale in which we just have this local propulsion. And in that limit, we were looking to see whether we could try and represent some of the chaotic, some of this positively affluent exponent, the chaotic dynamics of the system in terms of a stochastic forcing. There's a lot more work to be done there. We mainly just asked the question, but that's something which I'm very much interested in exploring in general, is how can one use stochasticity to explore high dimensional dynamical systems like this one. So that's a really important question.
Excellent, thank you. And finally, do experimental observations match the theoretical results you have highlighted in your work?
Yes, so some of the the work that I talked about earlier, for example, with the Landau levels, the agreement between the theory and experiment is spot on, is really impressive. And for very simple models as well, not ones which throw the kitchen sink at the problem. And then in a vast number of settings, so I've been working on the problem with the droplet interacting with the submerged cavity. There are some limitations to the model, all models are wrong, but again, there are very similar, at least qualitatively, need to check quantitatively, the agreement between the dynamics of the experimental system and theoretical models. In general, it's very favorable agreement.
Excellent. Thank you very much, Dr. Durey. I believe this marks the end of our plenary talks for the Early Career Mathematicians Spring Conference 2021.